Hello everyone, in this video we are going to discuss about modern periodic law and the present form of periodic table from the chapter 3 classification of elements and periodicity in properties class 11 chemistry. See, we will be discussing about Moseley's classification of elements. We will be discussing the modern periodic law, long form of the periodic table, the periods, groups, etc. See, when Mendeleev developed his periodic table, chemists knew nothing about the internal structure of atom. In 1913, an English physicist, Henry Moseley, he observed regularities in the characteristic X-ray spectra of elements. A plot of square root of frequency, that is nu is actually the frequency of X-rays emitted. So a plot of square root of frequency of X-rays emitted against the atomic number that gave a straight line, and not the plot of root nu, which is the frequency of the X-rays emitted versus atomic mass. That is, the graph of square root of frequency versus atomic number was a straight line, but the graph of square root of frequency versus atomic mass, that was not a straight line. So, Moseley showed that the atomic number is the fundamental property of an element than its atomic mass. See, Mendeleev's periodic law was accordingly modified, and now we have modern periodic law. See, modern periodic law, he actually stated this law as the physical and chemical properties of the elements are periodic functions of their atomic numbers. So, Mendeleev's periodic law was accordingly modified by Moseley, and we have modern periodic law, which actually is stated as the physical and chemical properties of the elements are periodic functions of their atomic numbers, not their atomic masses. So, based on the periodic law, numerous forms of periodic tables have been proposed. The most commonly used is the long form of periodic table. In this long form of periodic table, the horizontal rows are called as periods, which Mendeleev called as series, and the vertical columns are called as groups or families. See, the modern periodic table contains 7 horizontal rows called periods and 18 vertical columns called groups or families. See, in this periodic table, the hydrogen has given a particular position at the top center. That is, you see, this is the long form of the periodic table of elements. See, in this modern periodic table, we have 7 rows. That is 1, 2, 3, 4, 5, 6, 7. And these 7 rows are actually called as periods. And we have 18 vertical columns, 1, 2, 3, 4. Okay, 18 vertical columns are there, and these 18 vertical columns are called as groups or families. And in this modern periodic table, there are 7 horizontal rows, 1 to 7. And there are 1 to 18 vertical columns which are called as groups of families. And you see, in this modern periodic table or long form of periodic table, the hydrogen has given a special position. Okay, that is, hydrogen has given a particular position which is at the top center of this periodic table. You see, there are 7 periods in the modern periodic table, and the period number corresponds to the highest principal quantum number of the elements. That is, if you consider the first period, we have hydrogen and helium. Okay, these two are the elements in the first period, hydrogen and helium. So you see, there are 2 elements in the first period, and their subshells filled, you see, hydrogen, its atomic number is 1, so 1s1 electronic configuration, and for helium, its atomic number is 2, so 1s2, that is its electronic configuration. So the subshell filled in these 2 elements, that is 1s. And you see, this period is a very short period. Now, if you consider the second period, in the second period, we have elements from lithium to neon. Okay, so you see there are 1, 2, 3, 4, 5, 6, 7, 8. There are 8 elements in the second period. Okay, so you see their electronic configuration. See, their subshells will be filled like 2s and 2p subshells are actually filled. From when we write the electronic configurations for lithium to neon, the subshells filled will be 2s and 2p. Okay, and you see it is a short period. Similarly, if you consider the third period, we have from sodium to argon. There are 8 elements in the third period. And you see the the subshells filled are for sodium it is 3s. Then for aluminium 3s 3p. Then when you come to here chlorine 3s 3p, argon 3s 3p. So the subshells filled are 3s and 3p. And you see it is also it is also a short period. Okay, now when you look at the fourth period from potassium to krypton. So you see actually there are 18 elements. From potassium to krypton there are 18 elements. So it is a long period. Okay, and what about the subshells filled? For potassium 4s subshell, 4s1 is actually there. For calcium 4s2, so 4s subshell is filled here. Then when you come to krypton 4s2, 4p6. Okay, so 4s and 4p both are completely filled. And when you come to this zinc 3d10. So the maximum number of electrons possible in the subshell is 10. So 3d subshell is also filled. Okay, so you see when you consider the fourth period, we have the elements from potassium to krypton. There are 18 elements and the subshells filled are 4s, 3d and 4p. And you see it is also a long period. Now when you look at the fifth period, okay, that is from rubidium to xenon. Okay, so here also we have a total of 18 elements. It is also a long period. And the subshells filled are, you see 5s is filled here, 5p is filled here. Okay, 5s and 5p are filled here. And when you come to this cadmium, 4d10. So 4d is filled here. Okay, so the subshell filled here are 4s, 3d and 4p. Okay, similarly, when you look at the sixth period, it is from cesium to radon. Okay, so here you see from cesium to radon, you see how many elements are there? Total, actually 32 elements are there. That is when you look at this period, sixth period, from here to here 18 elements are there. And the rest of the sixth period is actually given here. Okay, as transition elements which is actually given here. So from cesium to radon, 18 elements are there. Then plus these elements are also there. 14 elements are there actually in this period. So total 18 plus 14 which is actually equal to 32. So the elements, the number of elements in the sixth period is actually equal to 32. It is actually one of the longest periods. Okay, and when you look at the subshells filled, you see here 6s2 is filled. 6s subshell is filled. When you come to this Au gold 5d10. So 5d subshell is filled here. So 6s is filled. 5d10. So 5d subshell is filled here. Okay. Similarly, when you look at here HF 4f14. So 4f is completely filled here. And when you look at here radon 6p6. So 6p subshell is also completely filled here. So this is one of the longest periods. Similarly, when you look at the seventh period, francium to organazone, and here also we have 32 elements. It is also one of the longest periods. That is sixth period and seventh period are longest periods. That is for the period 7, we have 18 elements here and the rest of the 14 elements are given here. Okay, so 18 plus 14 total 32 elements are here. And what are the subshells filled? Here you see 7s2. So 7s subshell is filled. Okay, and actually in the case of the 7th period elements, 7s subshell, 5s subshell, 6d and 7p subshells are completely filled. When you write the electronic configuration of each element, you can understand that. Okay, so 6th period and 7th period are the longest periods. Okay, now you see, here we have, when you consider the 6th period, 18 elements are given here and 40 elements are actually given here as a separate row. Okay, similarly, for the 7th period, 18 elements are given here and the rest of the 14 elements are given here as a separate row below the main body of the periodic table. So you see the 14 elements of the 6th period and 14 elements of the 7th period are placed in separate rows below the main body of the periodic table, and these two together are called as inner transition elements. Okay, these two together are called as inner transition elements. And you see the 14 elements of the 6th period, they are actually called as lanthanoids or lanthanons, that is from cerium to lutetium. These are actually also called as rare earth elements. Similarly, the 14 elements of the 7th period, they are called as actinoids or actinides or actinons. The 7th period is actually from thorium to lawrencium. Okay. Now you see the elements having similar outer electronic configuration in their atoms are arranged in vertical columns called as groups or families. Actually, when you look at the modern periodic table or the long form of the periodic table, you see the elements having the similar outer electronic configurations are arranged in vertical columns, and these vertical columns are called as groups or families. And you see in our periodic table there are 18 groups. First group, second group, then third, fourth, and similarly we have 18 groups here. And according to the recommendation of IUPAC, that is actually the International Union of Pure and Applied Chemistry, according to their recommendation, the groups are numbered from 1 to 18, replacing the notation, the older notation of groups 1A, 2A, 3A, 4A, etc. So the older notation for groups were 1A, 2A, 3A, 4A, 5A like that. And according to the recommendation of IUPAC, these names are replaced with the digits 1 to 18. And you see, due to the similar outer electronic configuration and same valency, the elements present in the same group have similar properties. That is, when you look at the first group, here we have lithium, sodium, potassium, rubidium, cesium and francium. The outer electronic configurations are here, given here 2s1, 3s1, 4s1, 5s1, 6s1, 7s1. So you see all the outermost electron is in the s subshell, and only one electron is there in the outermost level. So all these are arranged in the same group, which is called as group 1, because only one electron is there in the outermost shell. Okay, and these elements in the same group will have similar properties. So the general outer electronic configuration of the first group elements, that can be written as NS1, because you see for lithium it is 2s1, for sodium it is 3s1, 4s1, 5s1 like that, no? So here we can write it as NS1. And the first group elements are actually called as alkali metals. Now when you look at the second group elements, here we have beryllium, magnesium, calcium, okay, strontium, barium, radium. So here you see the outer electronic configurations are like 2s2, 3s2, 4s2, 5s2, etc. So in general, their outer electronic configuration can be written as NS2. This N is the principal quantum number, which can be 1, 2, 3, 4, 5, etc. And these elements in the second group are actually called as alkaline metals. You see the outermost electron number is 2, and that group is named as group 2. Okay, now when you look at the groups 3 to 12. Okay, we are considering the group 3, 4, 5, 6, then to 12. That is, here we have 4 rows of elements in this group 3 to 12. So you see, these elements are actually called as transition elements. Their outer electronic configuration, here you see for scandium, it is 3d1, 4s2. Okay, so you see 3 is actually 4 minus 1. Okay, similarly when you look at chromium, it is 3d5, 4s1. So 3 is actually 4 minus 1. So their general electronic configuration can be written like this: n minus 1, d raised to 1 to 10, ns 0 to 2. Okay, that is for scandium it is 3d1, 4s2. So 4s2. So n is 4, 4s2. Then 4 minus 1, 3D. 1 to 10 no, for scandium it is 1. So 3D1. Okay, now when you look at the, when you look at this, the third group, the outermost electron, no, 3D1, 4s2, 4D1, 5s2, so 1 plus 2, 3. So that is why these are in the third group. Okay, similarly, when you look at the 13th group, boron, aluminium, gallium, indium, thallium and neonium. So when you look at this group, 13th group, their outer electronic configuration is like 2s2, 2p1, 3s2, 3p1, 4s2, 4p1. So 2 plus 1, 3. Okay, and it is the 13th group. So you just want to, from 13 to 18, you just want to add 10 with the outermost electron number. You will get the group number. So 3 plus 10 is 13. Okay, so their general electronic configuration can be written as ns2, np1, and this group is actually called as boron family. It starts with boron, so this group is actually called as boron family. When you look at the 14th group, here we have carbon, silicon, germanium, okay, then tin, lead and flerovium. So their general outer electronic configuration is like ns2, okay, np2, and these are actually called as carbon family. That is, group 14 is actually called as carbon family because it starts with carbon. Okay, similarly, when you look at the 15th, 16th, 17th and 18th group, you will get these outer electronic configurations, and you see the group 15, that is actually called as nitrogen family. It starts with nitrogen. Group 16 is actually called as oxygen family. It starts with oxygen. Group 17 is called as halogen family, which starts with fluorine. And group 18, helium, neon, argon, krypton, xenon and radon. Also we have organozone here, OG. Organozone is also here actually in group 18. So these elements are actually called as noble gases. So in this video we have discussed about the modern periodic law and the present long form of the periodic table. I hope it is clear to you. All other videos are available from this chapter are available in the playlist. Thank you.